In this problem, Mr. Ott is in a slingshot. He's shot at an angle of 35 degrees and he's moving 25 meters per second out of the slingshot. Here's how that information fits the diagram. If we assume level ground, then the point of launch is the point of return, and there will be no change in vertical position from the beginning moment to the ending moment. It'll start at the 0 level, it'll end at the 0 level. And delta x is the range, how far Mr. Ott will fly horizontally. Key to the solution will be a table of horizontal and vertical values, as well as the trigonometry needed to figure out the initial velocity horizontally and the initial velocity vertically as Mr. Ott is launched from the slingshot. So the sine of 35 degrees is the opposite over the hypotenuse, and everything is a number there except for v0y, and when we solve for that we get 14.34 meters per second. So that is the initial velocity in the vertical direction at the start of this projectile. And solving for the adjacent side and that triangle with the cosine of 35 as the initial velocity horizontally to be 20.49 meters per second. Now let's start filling in the table. For horizontal values, initial velocity, we just calculated that, 20.49. The final velocity, that means when he gets back down to the ground. Well, we know that horizontal velocity doesn't change. It's constant because there's no horizontal forces. How far does he go? That's what we really want to know. That's the change in horizontal position. We do not know that. We want to know that. Acceleration, horizontally is 0. All right. If we want to calculate delta x, we could be done if we knew the horizontal velocity, which we do. Multiply that by the time. And for a constant velocity object, that's how you get displacement, how far it's going, but we don't know time. So we're going to want to figure out time. Vertically, starting velocity we calculated was 14.34. And then the final velocity, in this case, because of its symmetry, it's going to be going the same speed, but in the opposite direction at the other side. The change in position from beginning to end, vertically it starts at the 0 level, it ends at the 0 level, so that's 0. And acceleration is due to free fall. That's the situation of a projectile, is it is in free fall. Force diagram is for its flight is just gravity down, our definition of free fall. So we do have 1, 2, 3, we have 4 things we know. We can figure out anything we want when it comes to the vertical motion. This kinematic equation will allow us to calculate t, and we want to solve for t, so we rearrange it to solve for t, and it equals final velocity minus initial velocity in y divided by acceleration in y, that is, and it turns out to be 1.2 seconds of time in the air for Mr. Ott. So, Mr. Ott's range, delta x, that is a horizontal quantity, so it's constant velocity. And we know for something moving constant velocity, we multiply its velocity time the time that it's moving to get how far it's gone. So in this case, horizontal velocity of 20.49 meters per second times 1.2 seconds equals 24.5 meters is his range. Now, his maximum height would occur in the middle of the flight, which would be at the midpoint time and at the midpoint x. So this point it's a different point in its flight, so we need to reanalyze the vertical motion for that point. The starting velocity is the same, hasn't changed. Now this value, the velocity at the peak, the vertical velocity at the peak is 0. It's just as if you throw something up at its peak, it has 0 velocity before it starts to come back down. That is the vertical velocity at the peak. We want to figure out the change in position from where it started to that point, which is the peak. That's what we look for. That's delta y. And of course, the acceleration vertically is the same. So delta y equals v squared minus v0 squared over 2a. Where'd that come from? Well, one of the kinematic equations is v squared equals initial velocity squared plus 2 times a x or y, depending on what you're using. So starting with that, let's end up with that right there. Which, when we substitute in our values there, we end up with 10.5 seconds.